In a previous video, we introduced projectile motion, and I want to look at the kinematic equations that we'll be using and see how those apply when we have two-dimensional projectile motion. So again, we're going to be thinking of a projectile. It could be a ball, it could be a bullet, it could be a dart flying through the air towards a dartboard. Anything that's moving through the air is considered a projectile. So after it's thrown, it has this parabolic path, if it would be a ball, for example. And how will we describe this motion? So from a previous video, we discussed that the velocity in the horizontal direction is independent of the velocity in the vertical direction. So here at the beginning of the object's flight path, it will have some large initial vertical velocity, so this would be Vy, and it will have some horizontal velocity Vx. And we know that Vx remains constant throughout the entire path of the object. Vy is going to change, so in the next instance of time, you'll have some smaller vector pointing upwards, but the vector that's pointing horizontally is going to remain the same because it doesn't change over time. There's only acceleration in the y direction because g, the acceleration due to gravity, is pointing downwards. So how do we represent this then using kinematic equations? Well, because it's a vector and it has vector components, we have to treat each dimension independently. So we're going to have equations of motion for each dimension. You'll have equations of motion for the y direction and equation of motion for the x direction. So let's start first with the y direction. That's actually the most complex, but it's going to be using the equations of motion that we've already learned. So looking then at the kinematic equations, the first one is the kinematic equation for velocity. And we're just interested in the vertical component at this point. So vertical. So first we have some velocity final. We've seen this before, but now we're saying it's in the y direction. Equal to the initial velocity in the y direction plus the component that's being affected by acceleration. So our acceleration is gravity, and we multiply the gravity acceleration times time, and this gets us the changing component of velocity. So we've seen this exact same equation previously. It instead was just v final equals v initial plus at. So now we're speaking about it just in terms of the vertical components, and our acceleration now is g. And the second equation of motion then is the change in position, which we've seen this before. So delta y, and I'm interested in the initial velocity in the y direction times time. Velocity times time gets me the correct units for displacement, plus the component that's affected by acceleration, and it's 1/2 gt squared. This is the triangular component of the velocity versus time graph just for this vertical component. So these two equations look a little different because we've added some subscripts, but they're exactly the same as ones we've learned previously. This is a kinematic equation for velocity. This is the kinematic equation for position. And this describes how the velocity changes in the vertical direction and how position changes in the vertical direction. So what about the x direction? What about the horizontal component? And in the textbook, it lists just one equation, and it doesn't go into much detail. And I'm going to show you why it only lists one equation. Well, first, what is, if we look now, we're looking at this velocity equation. So let's just write it out. Let's say v final in the x direction equals v initial in the x direction plus some acceleration times time. Notice I did not put G here because G is only working in the vertical direction. G has nothing to do with the horizontal component. Okay, so what is my acceleration horizontally? Well, again, we discussed that the horizontal components are equal at any point in time, so there is no acceleration. If this Vx stays the same for every period of time, then there's no acceleration in the horizontal direction. So this is a equals 0, and that term goes to 0. And we can see here that the initial velocity in the x direction is exactly the same as the final velocity in the x direction. And that's exactly what we want. Again, that has to be the case if the velocity in the horizontal direction is to remain the same at every point along this path. Well, then of course the final has to equal the initial. It doesn't change. So we don't really even need this equation because, well, the final equals the initial. We're not going to be solving for some difference between the final and the initial velocity. Okay, so what you will see in the textbook on page 40 is you'll see this delta x equals v sub x times t. And again, we can add this component with an acceleration on there. This would not be wrong. But again, I'm adding an a instead of a g because the g does not function or work at all horizontally. So again, what is my acceleration horizontally? Well, it's 0. Just as it is here in this velocity equation in the x direction, the acceleration is still 0. It doesn't change because the acceleration is a constant. G equals 9.81 meters per second squared. And this only occurs in the vertical direction. It has nothing to do with this horizontal component. So in the book, all it lists is this equation right here. Delta x equals v sub x times t. It does not list this first equation, and it doesn't list this component over here that tells us the acceleration and how that affects the change in position, because there is no acceleration in the horizontal direction. So we'll just be working with basically these 3 kinematic equations, and those will help us describe pretty much all the motion of a 2D projectile motion problem. We're going to be using these 3 equations quite a bit, and solving for one condition. For example, sometimes we'll first solve for time using the horizontal equation because this equation is very simple. And the velocity remains the same throughout the trajectory of this projectile in the horizontal direction. And we'll use that fact often to solve for time. We can use just this horizontal component to solve for time, and then use time. This t remains the same whether you're working horizontally or vertically. The amount of time that the object is moving is not independent of these 2 situations where you have a vertical and horizontal. The time is shared. It's the same. I don't have some t1 and t2 over here. This t is the same. So we'll exploit that fact when we're solving problems.